Hello, everyone, and welcome back. My name is Mr. Cobalt, and in this video, I'm going to be going over how to estimate the standard change in free energy for a reaction. Now, in a previous video or previous couple of videos, I showed you how to calculate the standard change in free energy of a reaction, and I did a couple of problems. But in this case, in those cases, we were at the standard temperature, which is 25 degrees Celsius. So when I did this reaction in a previous video, it was at 25 degrees Celsius. But notice that we are now at 125 degrees Celsius. So we're not at standard temperature. So what do? So here I have written down that here was the standard change in free energy of this reaction at 25 degrees. It was negative 70.9 kilojoules. So we're going to see how the standard free energy change of this reaction, same reaction at 125 degrees compares. But first, how do we do this? How do we calculate it? Well, we calculated the exact same way as we calculated it last time. So the reason for that is because although technically speaking, the equation that we're going to use, the standard free energy change of a reaction, is equal to the standard enthalpy change of a reaction minus the standard entropy change of the reaction multiplied by the temperature, even though this equation technically only applies to reactions at the standard temperature, 25 degrees Celsius. At other temperatures within a limited range of temperatures, we can use this to estimate because even though we're changing temperatures, the change in entropy, the standard change in entropy, and the standard change of enthalpy under a limited range of temperature changes very little compared to the larger change in temperature. So we can use this to get a good estimation, even though it might not be exact, right? So we're going to do the same thing we did before. So we're going to get the standard enthalpy of the reaction. So we're going to use the same equation. So that's going, oops, sorry. So we have the standard enthalpy of the reaction is equal to the sum of the products, right? So the sum of the products multiplied by their coefficients. So this is going to be the standard heat of formation of products minus the sum of the reactants. So the number of the coefficient multiplied by their standard heats of formation of reactants. So once again, we plug that into our equation. So that's going to be product. We only have one product, so it's going to be 1 because of the coefficient 1 multiplied by the heats of formation of SO3, which is negative 395.7. So negative 395.7. Oops. And again, we should have our units in here. This is going to be kilojoules per mole. So kilojoules per mole. And then we're going to do our reactants. So we're going to subtract out the sum of the reactants. We have 2 reactants. So the first one is SO2. We have 1 of those. So we're going to multiply by 1. And then the standard heat of formation of SO2 is negative 296.8. So negative 296.8 kilojoules per mole. And then add to that of oxygen. So oxygen has a 1/2 there, so 1/2. And then we're going to multiply that by 0 because any element in its standard state is going to be 0. The heat of formation, the standard heat of formation is 0, so that's going to be 0. And here we go. We calculate that out as just like we did before, and that comes out to negative 9.89, 9.89. Oops, sorry. 9.89. Yeah, 90. I'm sorry. I don't want to skip a step. So 98.9 kilojoules, but we want to convert that to joules because our standard entropy is in joules. Entropy is measured in joules per Kelvin. So we want to convert this to joules using our conversion factor. So 1 kilojoule is equal to 1,000 joules. I have kilojoules on bottom so they can cancel out. And now I have joules. So this is going to be negative 9.89 times 10 to the fourth joules of energy. Now next we're going to do the entropy. So same exact equation, but now we're dealing with entropy. So that's going to be delta S, standard delta S of the reaction is equal to, again, the sum of the products minus reactants. So it's going to be the standard entropy of products minus the sum of the standard entropy of reactants. So again, plug that in, use our equation. So products first. So I only have one. So 1 SO3, the standard entropy of SO3 is 256.8. So that's going to be 256.8 joules per Kelvin. And then we're going to subtract out our reactants. We have two reactants again. So we have 1 for SO2. So 1 times SO2, the S is 248.2. So 248.2 joules per Kelvin. And then we're going to add to that oxygen. This time oxygen has a positive 205.2 joules per mole Kelvin. Oops, sorry about that. I forgot my mole here. So mole Kelvin, and then here I have 1/2 for the oxygen. So I'm going to multiply that by the 205.2, 205.2, and again, that's joules per Kelvin, or mole Kelvin. And then I'm going to close that out. So the reason it's mole Kelvin, because moles times moles is going to eliminate, and then we're just going to end up with joules over Kelvin, which is the unit we want. Okay, so we go ahead and calculate this out, and what we get is negative 94.0. So we get a negative 94.0 joules per Kelvin. So here's our delta H, or standard enthalpy of the reaction, and here is our standard change in entropy. So now we can go ahead and plug those into the equation, including our temperature. But remember, we have to change temperature to Kelvin. So we add 273, and that's going to give us 398 Kelvin. 398 Kelvin. So then we plug everything in. So here we have the standard free energy of the reaction is equal to, and then we're going to have our delta H, standard enthalpy of the reaction, so negative 9.89 times 10 to the 4. And again, that's joules and then we're going to subtract that delta S of the reaction, standard entropy change of the reaction, that's negative 94.0. So negative 94.0 joules per Kelvin multiplied by the temperature. So again, let me fix this to make it clear. So we're subtracting, but then this is negative, so negative 94.0 joules per Kelvin. We're multiplying that by the temperature, 398 Kelvin. Okay, so we have 398 Kelvin. We multiply all this together and we get this is equal to, what did I get? Negative 6.15. Negative 6.15 times 10 to the 4 joules. Because here Kelvin cancels out, we're left with joules. And this is, if we convert this to kilojoules, it would be 61.5, 61.5 kilojoules. Negative 61.5 kilojoules. So again, still spontaneous at 125 degrees Celsius. If we compare this, so our standard change in free energy here for 125 degrees is slightly less negative than at 25 degrees. So the more negative the value of your delta G, your standard free energy of the reaction, the more spontaneous it is. So since at 25 degrees we have a negative 70.9, but at 125 degrees Celsius we have a negative 61.5. So it became less negative, therefore it's less spontaneous at this higher temperature. So I hope that was helpful. This is how you would estimate the free energy change, the standard free energy change of a reaction at other temperatures other than 25 degrees, which is standard. So if this was helpful in any way, if you enjoyed this video, then please, by all means, like the video, share it with your friends, hit that like button over there somewhere, and please, by all means, subscribe to my channel, hit that notification bell, click all so you can be notified by all the videos I put out, and finally put a comment down below. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me and have a great day.